Hi, I'm Michelle Lochner, and I'm a senior lecturer at the University of the Western Cape with a joint scientist position with the South African Radio Astronomy Observatory. And I'm going to be talking to you today about anomaly detection in astronomical data. This is work I've done with a number of collaborators, but particularly with my colleague Bruce Bassett, who's the head of the Surveyor Data Science team. So let's set the stage for a minute. And I want to do this by talking about two telescopes, future telescopes that I'm heavily involved in and really excited about. The first of which is the Vera C. Rubin Observatory, what used to be called the LSST. And this telescope is a 10-meter class optical telescope built in Chile. And it's an amazing instrument because it's incredibly deep. It's got a very wide field of view and very fast. So it's the 10-year survey is going to do a very impressive range of science, everything from asteroids to cosmology. But I think one of the most interesting technical challenges represented by LSST is the transient science. So here's an example of a simulation where every dot is a new supernova that will be discovered. And so at the end of the 10-year survey, we're talking about somewhere between 500,000 and 1 million really beautiful, well-measured type 1A supernova light curves, which is quite impressive when you think that the original dark energy discovery was made with just 42. And what's an even bigger challenge is that the number of alerts that will come out of LSST every night will be in the vicinity of 10 million. And if even just half of these are astrophysically interesting, you know, there's a real challenge in dealing with this incredible data rate. On the other side of the spectrum is another telescope I'm obviously very excited about, which is the Square Kilometre Array. This will be the biggest radio telescope ever built. The final design is kind of still in flux and still fairly far in the future. But I think what everybody agrees on is that the data rates that are going to come out of this thing are stupidly large. We're talking about petabytes a day. And that's the raw data, but even the processed data starts to push the limits of what our current algorithms can do. You're talking about a survey of over 1 billion galaxies, thousands of coherent and incoherent radio transients. So the SKA represents the kind of matching data challenge in the radio. And although these are both future telescopes, we are starting to be pushed with current what are called precursor telescopes. So in South Africa, we have the Meerkat telescope, which is a 64-dish array. And it's already taking very beautiful radio data, which, although it's not of the kind of rates we'll expect from the SKA, it's at the point where it's getting a little challenging to download the data onto your laptop and reduce it there. So we're having to rethink how we do data analysis. And I think this is true across the board in astronomy. And so, of course, we're facing this data explosion. And for many of us, I think we're quite convinced that the solution to many of the problems in trying to work with such large quantities of data is machine learning. Now, I would say about 99% of the time when people talk about machine learning, they're talking about specifically supervised machine learning. So this is an example for where, for instance, you've got some data belonging to two different classes and you're trying to learn the model that automatically divides the two different classes. And in the case of supervised machine learning, you need a training set. You need a set of labeled data that allows you to train your algorithm. And the majority of machine learning problems fall into this category. But I'm particularly interested in unsupervised machine learning, which is the case where you don't have any labels, and is particularly interesting for the area of anomaly detection. Okay, so what is anomaly detection? I think everybody has a pretty intuitive idea of what it is an anomaly. An anomaly is anything that's rare or unusual. In the case of astronomy, there are many examples. For instance, strong lenses in the image plane, gravitational waves in the fast radio bursts, although you know these actually might not be that rare events. And these are all what I would call known unknowns. They're rare events, but we know about them and we know how to look for them. But I think what's really exciting, and I'm sure what every scientist is really excited about is the unknown unknowns, the truly new scientific discoveries that nobody was really expecting. And I think a great example of this is the pulsar discovery in the 60s. And I like to highlight this because it took a very bright young graduate student to manually, laboriously look over her data and notice something unusual in order to make this great unexpected discovery. And the question that I ask myself is, in this era of enormous data rates, how are we going to do this? How are we going to make new scientific discoveries when there's 10 million alerts every night? Or when there's a billion galaxies in your catalog? When the data becomes so large that it's almost inconceivable that all of it is going to be looked at by a human being. And so this is where machine learning for anomaly detection comes in. So machine learning algorithms, there are some existing anomaly detection algorithms. They differ from supervised learning, of course, because we have no training data. We're looking for, we don't know what we're looking for. We don't have any labels. So what these algorithms tend to try to do is simply learn a model for kind of what normal is. And then any new object that comes in that's far away from the norm would get a high anomaly score. A couple of examples of existing anomaly detection algorithms is isolation forest, which is based on the very popular random forest supervised machine learning algorithm, which basically tries to perform a series of cuts in feature space that would isolate individual objects. And objects that are more anomalous are easier to isolate. Then there's a local outlier factor, which is a density-based algorithm, which essentially says any object in a low-density region of feature space would be more anomalous. In our group at Soraya, we've developed a couple of new anomaly detection algorithms. I was involved in this one. This is called BADAC. And what's interesting about BADAC is, first of all, it's simultaneously an anomaly detection and a classification algorithm. And it's Bayesian and is able to incorporate uncertainties in the data. And I think this is important as we start pushing into the low signal to noise regime, where it's very easy to get a lot of false positives from the noise. By incorporating the uncertainty, you can alleviate a lot of this. And then I just want to mention DRAMA, which is a deep learning-based anomaly detection algorithm. And you can look at the details in the two papers here. But the thing is that what Bruce and I realized is that anomaly detection alone isn't actually enough. So here's some examples of some work I did with a student, Sarah Webb, and I'll mention this again a little bit later. And this was on some deeper, wider, faster, or DWF data. So DWF is trying to search for rare, fast transients, basically. And so Sarah came to me with I think about 80,000 light curves that had never been looked at by a human. And so we were doing some unsupervised learning on it, and we ran anomaly detection on it. And the algorithm did a good job. It picked out a bunch of stuff. But what we found is these two examples, for instance, are just instrumental effects, whereas these two are real sources. But both look like anomalies to the algorithm. So and of course, we're not interested in the instrumental effects. We're interested in the real sources. So there's this idea of relevance. Not all anomalies are relevant. And what we realize is this is actually quite subjective. So it's not even just trying to get rid of artifacts. I may be interested, as a scientist, may be interested in peculiar supernovae, say, but I don't care about weirdly behaving variable stars. Whereas a different scientist would have a completely different interest. And it's challenging because, of course, you may not really know beforehand what it is that you're actually looking for because, of course, these are anomalies. You don't necessarily have training data. So there's an idea of relevant versus irrelevant anomalies, which is inherently subjective. So to deal with this problem, we implemented a novel active learning approach. So active learning is where you combine the intuition and the knowledge of human beings with the raw processing power of machine learning. And there's many different ways of doing this, and we came up with a new approach to try to solve this problem. And we built it into this framework called Astronomaly. And I think I'm the most proud of the name more than anything else. So what is Astronomaly? Astronomaly is a framework that has a Python backend that does all the heavy lifting, coupled to a web interface written in JavaScript. So the backend does all the steps that you'd kind of expect from a machine learning framework. It reads in the data, and the nice thing is that it can more or less take any type of astronomical data. So whether it's images, time series, spectra, it's fairly agnostic. It does a feature extraction step, and this is the part that's really critical, because the features that you choose are going to dictate the sorts of anomalies that you'll be sensitive to. So for instance, in the example I'm about to show you, I chose features that were quite sensitive to morphology. So I would pick up morphologically strange objects, but not perhaps objects with weird colors. So that's just an example. So we read in the data, do feature extraction. There's a number of anomaly detection algorithms, including some of the ones that I mentioned earlier. And then there's the active learning approach here. Now, in order to do this active learning step, we needed to get labels from the human. And that's where this web interface comes in, where you see you can very quickly look through your data and give it scores based on how relevant each object is to you. Oh, and I should just mention that the paper is available here and the code is already publicly available. So here's some examples using Galaxy Zoo data. So just examples of image data. This is a data set, it's a citizen science project, and it's a data set of about 60,000 labeled galaxies, mostly from the SDSS data. And here I'm just flipping through some random examples just to show that the average galaxy in the data set is a fairly boring elliptical or spiral galaxy. Now, if you run the machine learning and then you order all 60,000 galaxies from most anomalous to least anomalous, this is what you get. And you can see that it does a reasonably good job of picking out merging galaxies, galaxies with tidal tails, interacting galaxies, things with interesting morphology. But if you look carefully in the first 20 or so that I'm flipping through, there are a couple of artifacts, things that I might not be interested in. And this is where the labeling comes in. So if you look carefully, you'll see that there's these buttons that are lighting up with different numbers. I'm labeling the data based on how relevant I think each object is. I can then retrain it using our active learning algorithm, and now sort it again according to the most relevant anomalies. And what you see is that it tends to get rid of most of those artifacts and prioritize the types of objects that I'm personally more interested in. This is just to show a little bit more numerically how the active learning works. So this is as you go through the ranked list, you can ask yourself how many true anomalies are detected. The definition of anomaly, particularly in this data set, is a little bit arbitrary, but nevertheless, we made some definition. And just to show that the active learning really does improve the number of anomalies that you see, particularly early on in the ranked list. Okay, that's all very well and good, but we really wanted to see if how well our active learning was doing. And so we simulated some synthetic data. And this is, instead of image data, this is now something that looks a little bit more like a time series, but it's completely made up. So here you can see we just drew them from some mathematical functions. This is the sine wave, this is the parabola. And these are the two boring normal classes. So 99% of the data belongs to these two. On the left, what you're looking at is called a TSNE plot. This is a low dimensional representation of the high dimensional feature space. So you should think of it that each point in this plot corresponds to a single object in my data set. So the two classes that we're looking at mostly belong to these two clusters here. These remaining clusters that have different color are the anomalous classes. So there's 3 of them, and together they make up just 1% of the data. And what we did was to try to evaluate this active learning approach, we had to imagine that one of these classes was more relevant than the others. So completely arbitrarily, we decided this sum of sine waves class was really the most interesting thing that we've ever seen before in our lives, while this Gaussian was really boring and we really didn't want to see any more of it. And the step function was sort of somewhere in between. Okay, so let's run this again through Astronomaly. It's all the same interface. And here's again random examples. And not surprisingly, if you do a random draw, you mostly get the boring classes. But then if you run the machine learning and you order again by most to least anomalous, well, it does a pretty good job. Everything in this top 20 that I'm showing you certainly is an anomaly. But you can see that there's no examples of that class that I said was the most interesting. Instead, it's showing me these boring Gaussians. So we run our active learning algorithm, and you can think of this almost like a recommendation engine. You know, I'm as if you were watching Netflix or using Amazon, and you're trying to train this thing to recommend things that are actually interesting to you. So by providing a fairly small number of labels, in this case, I think I gave it about 100 labels, which takes a couple of minutes to do with this interface out of the full 50,000 data set. So just by providing a couple of labels and running our active learning algorithm, you can see if I order it by most to least relevant now, that now those sum of sine waves objects are popping up a lot more, and we don't see any Gaussians. The Gaussians have been downweighted and shoved further down the list. We still get some of those step functions because we kind of said we're sort of interested in those. Just to visualize what it is that we're actually doing, this is actually, again, another TSNE plot, but instead of points, I've now made it a heat map, where the lighter the color, the more anomalous the algorithm thinks that region is. And I've given it, the numbers here are the actual labels, the human provided labels that I've given it. So you can see initially, the raw machine learning algorithm thinks this part of feature space is the really interesting stuff. This part's also pretty interesting, but this part's actually kind of boring. By providing these labels, I'm giving these all a 5 out of 5, saying, actually, this region's really interesting to me and I don't care about this. And so the active learning approach basically just upweights this region of feature space and downweights this region. So if any new object comes in, it's not going to get a very high score, and it's over here, I'm not likely to see it. What's also incorporated in our active learning approach is the concept of uncertainty. So if a new object crops up with a high anomaly score that's in a region that's got no labels nearby, it's actually not going to get it's actually not going to get downweighted because we don't really know anything about it. So in that way, you're not going to miss things that you haven't seen before. But if something pops up that's similar to something you've seen before that you've downweighted, you're not going to see it. And so this really just makes much more efficient use of a human's time with the data. I want to finish off this talk with just a couple more examples of Astronomaly in action. So this is with Meerkat data. This is using essentially the same algorithm that I used for the optical data, but now for a really very different kind of data set. I took a very beautiful Meerkat image called the Deep 2 offset image, which is a deep image of a relatively empty patch of sky. And I chopped it up into little cutouts. And what you can see is that if I draw some random examples, mostly you just get noise and point sources. Whereas if I run the anomaly detection algorithm, what it starts picking out are morphologically interesting radio galaxies. And this is just a summary of some of my favorite ones that I've found. I wanted to mention again this DWF project that I worked on with Sarah Webb, an extremely bright student from Australia. And so she took this huge data set of 80,000 light curves, raw light curves that nobody has really analyzed. And she ran a clustering algorithm, so an unsupervised learning algorithm, to try to learn something about the dominant clusters in the data. And then she ran Astronomaly on the kind of unknown objects and was able to make a few, nothing Nobel Prize winning, but definitely make a few very nice discoveries. So, for instance, she picked up a few known variable stars, a few new variable stars that hadn't been seen before, and one quite interesting ultra-fast flare. So it really is a proof of concept that even with a fairly large data set, you can work through it quite quickly with these techniques. And finally, I want to mention real-time anomaly detection, because everything I've talked about up until now is as if you had a data set and you just analyzed it to get out the anomalies. But of course, in the era of ZTF and the Vera C. Rubin Observatory, it's real-time anomaly detection that's the really hard part and the really important part, because we have so little time to react to interesting transients. So this is work done with Daniel Mutkrishna, as a student at Cambridge. And what we did is we reasoned that we do know something about the various well-known classes of transients such as supernovae and AGN. And so we built a generative model that is able to predict the next points on the light curve based on the previous points, reasoning that if you have an anomaly and you try to make a prediction with generative models built from each of these classes and none of them fit, well, then it's going to flag as an anomalous event. So here's an example of a light curve where initially you can see that the likelihood is pretty high for all the classes, but pretty quickly it does something unexpected and the likelihood goes down for everything, the anomaly score goes up. And that's good because this is actually a peculiar 1A from the ZTF data. Okay, so basically to conclude, I think many astronomers are quite convinced that machine learning is a critical tool in facing the data deluge that's, well, here and is only going to get worse. And I think that if we want to ensure scientific discovery in this era, we need some form of automated anomaly detection, but we also need this, the human input is a critical step. And so the question is basically just how to use human resources as efficiently as possible. And so our answer to this is Astronomaly, which you can check out here. The paper is available and the code is of course available, and please feel free to contact me if you're interested in starting a conversation about this. Thank you very much.